Welcome to Talk Tensors.
Glad to be here.
It is incredibly exciting to have you joining us today.
Oh, absolutely.
If you are tuning in, you probably share our obsession with where the frontier of machine learning is heading.
Yeah, it's moving fast.
It really is. And right now, the entire community is completely buzzing about a monumental release.
That's an understatement.
Right. We are talking about a massive open-weight herd of models peaking at a staggering 405 billion parameters.
It's just a behemoth.
An absolute behemoth of a system. And you, as a fellow learner and tech enthusiast joining this conversation, you're probably wondering how this shifts the landscape.
Because it does.
Okay, let's unpack this. Because this isn't just, a big neural network.
No, not at all.
It is a fundamental disruption to the established hierarchy of artificial intelligence.
It really is a watershed moment for the field. I mean, if we want to distill the core thesis here.
Please do.
The single most important takeaway from this technology, it is a proof of concept on a historic scale.
Historic in what way?
It proves that by leveraging absolute unprecedented compute scale, combined with hyper-curated data and a surprisingly traditional architecture.
Which is the crazy part.
Right. Doing all that, an openly available model can match and even exceed the performance of the most advanced, closed-source proprietary systems in the world.
It fundamentally challenges the moat of the closed AI ecosystem.
Exactly.
I want to pause on that because it's a huge claim.
Yes.
The mission for our deep dive today is to get past the hype and the X threads.
Because there are a lot of them.
Too many. We are going to meticulously break down the dense architecture, the relentless data curation pipeline.
The data engine is fascinating.
And the sheer logistical nightmare of keeping a 16,000 GPU infrastructure from just melting down.
Literally melting down.
Right. We'll look at the real-world benchmark performance and the fascinating compositional approach used to give this model eyes and ears.
A multimodal stuff.
Exactly. We want to give you the complete, unfiltered technical picture today.
Sounds good.
But before we get into the silicon and the math, set the stage for us.
Sure.
Why does this 405 billion parameter milestone matter so much right now?
Well, to really appreciate the gravity of this release, we have to look at the narrative that has dominated the industry over the last 2 years.
Right, the accepted wisdom.
Exactly. The prevailing assumption was that open weight models where you can actually download the weights and run them yourself,
right,
they were fantastic for edge devices or for academic research or, lightweight enterprise tasks.
The smaller stuff.
Yeah. But the hard consensus was that if you wanted cutting-edge, state-of-the-art reasoning,
the really smart stuff,
you absolutely needed a proprietary closed model locked behind an API.
Because it was too expensive otherwise.
Exactly. The narrative was that the capital requirements and the engineering complexity of frontier models were simply too high to ever be open source.
And this release changes that.
This 405 billion parameter giant completely shatters that assumption. It proves you can have frontier-level intelligence running on your own infrastructure, provided you have the hardware to support it.
Provided you have the hardware. Which brings us perfectly to the architecture.
Right.
And this underlying philosophy of managing complexity. Because when you hear 405 billion parameters,
that sounds chaotic.
The immediate assumption is that the internal wiring of this thing must be wildly complex.
Using some highly experimental new design.
Exactly. But looking at the technical details, it's actually remarkably traditional.
What's fascinating here is the deliberate choice to avoid the current industry trend.
Mixture of experts.
Yes. If you look at the trajectory of top-tier models from other organizations, almost all of them currently use mixture of experts or MOE architectures.
Break that down for us briefly.
Sure. In a MOE model, you might have 1 trillion parameters in total.
Okay.
But for any given query, a routing mechanism only activates a small subset of those parameters.
The specific experts for that topic.
Exactly. The experts for that specific type of query. This is incredibly popular because it decouples the knowledge capacity of the model from the compute cost.
So you get the brain size of a massive model.
The electricity bill of a smaller one.
Let me jump in with some skepticism there, though.
Go for it.
If every major competitor right now is using mixture of experts to save massive amounts of compute during inference, why on earth would the engineers behind this model stubbornly ignore the biggest cost-saving trend in the industry?
It's a great question.
Because they went with a standard dense transformer architecture.
They did.
That means every single one of those 405 billion parameters is active during inference.
Yep.
When you send it a prompt, the entire brain lights up. That sounds incredibly expensive and risky.
It sounds risky until you look at the math of a cluster failure at this scale.
Failure.
The decision to use a dense architecture is purely about optimizing for maximum training stability.
Stability over efficiency.
During training, yes. When you are orchestrating a 16,000 GPU cluster, you are burning millions of dollars in compute time.
Right.
Stability is your absolute highest priority. Mixture of experts introduces immense routing complexities during the training phase.
Like what? What goes wrong?
Sometimes the router sends too many tokens to one expert, causing severe load balancing issues.
So some GPUs are working too hard.
And others are sitting completely idle. Or worse, the training process diverges entirely and just crashes.
And I imagine a crash isn't just a minor inconvenience where you hit restart.
Far from it. A crash at this scale is catastrophic.
Financially?
Financially and in terms of lost momentum. You have to locate the failed node among thousands, isolate it, roll back the entire cluster to the last safe state, and spin everything back up.
That sounds like a nightmare.
It is. Dense architectures, on the other hand, are incredibly well understood. We have been scaling dense transformers for years.
The simplicity scales predictably.
Exactly. They chose a stable architecture so they could push the parameter count and the data volume to the absolute limit without the model collapsing under its own complexity.
Okay, that makes perfect sense when you frame it around the sheer terror of wasting millions of dollars on a crashed training run.
Pure pragmatism.
But while the core is a traditional dense transformer, they did make a few crucial architectural tweaks.
It did.
I'd love to translate these into plain language for the listener.
Let's do it.
Let's start with grouped query attention, or GQA.
Specifically using 8 key value heads.
Right. What is the actual physical problem this solves inside the machine?
It fundamentally addresses the memory bottleneck during text generation.
Okay.
Let's visualize how a transformer works during decoding, which is when the model is generating text word by word.
Right.
To understand the context of the sentence it's writing, it has to store previous keys and values in its memory.
It's short-term memory.
This is called the KV cache.
Yeah.
Think of it like a person writing a highly complex essay. They need to keep their previous paragraphs actively in their short-term memory to ensure the new sentence makes sense.
But with 405 billion parameters, I imagine that short-term memory gets full very quickly.
It grows exponentially. For a model of this magnitude, the KV cache becomes so massive that the GPUs actually run out of memory bandwidth before they run out of mathematical compute power.
Oh, wow.
You are starved for memory, not math.
So how does grouped query attention fix that?
It solves this by forcing multiple query heads, the parts of the model asking for information,
Right.
to share a single key value head, which is the part storing the information.
Okay.
By standardizing exactly 8 key value heads, they drastically reduce the total size of the KV cache.
If I'm understanding you correctly, it's like having 8 researchers in a library.
Okay, I like this.
And they're all forced to share the same filing cabinet, rather than each getting their own massive redundant cabinet.
Yes.
It saves floor space.
That is a brilliant way to conceptualize it. It saves crucial memory space on the GPU.
Which means what, practically?
It means you can process significantly longer sequences of text, and you can serve more users simultaneously on the same hardware without hitting that memory wall.
It speeds up the inference process dramatically.
Exactly.
I always appreciate how these incredibly opaque mathematical tweaks ultimately just come down to traffic and storage management inside the silicon.
It really is just plumbing at a certain point.
Yeah. Another fascinating upgrade is the vocabulary size.
Right.
The technical specifications show they expanded it to a 128K vocabulary.
Which is huge.
From what I gather, it combines 100,000 tokens from a standard tokenizer with an additional 28,000 non-English tokens.
Correct.
It's essentially an upgrade to the model's alphabet, right?
Yes, and that upgrade has profound implications for efficiency.
How so?
Expanding the vocabulary improves what we call the compression rate. The data shows that this new tokenizer improved compression on standard English text from 3.17 characters per token to 3.94 characters per token.
So instead of spelling things out almost letter by letter, it has a massive internal dictionary of whole syllables and complete words.
Exactly.
I can read whole paragraphs in fewer glances.
Exactly the right visualization. So for every single token the model processes mathematically, it is actually digesting significantly more real-world text.
Meaning it's more efficient.
Right. For the exact same amount of electricity and compute power, the model gets to read a much larger volume of information during its training phase.
And what about those extra 28,000 tokens?
By carefully selecting those specifically for non-English languages, they boosted the model's multilingual performance dramatically.
Allowing it to understand nuances in other languages.
Without degrading its core English reasoning capabilities at all.
And reading more text efficiently leads perfectly into the discussion about the context window.
The context window is massive here.
This model can process up to 128,000 tokens at a single time. To put that in perspective for you, the listener, 128,000 tokens is roughly the length of a full novel.
It's a lot of text.
You can drop an entire book or a massive code base into the prompt box all at once.
And it remembers all of it.
Right. But to achieve this, the team had to tweak a hyperparameter called the rope-E base frequency, pushing it all the way up to 500,000.
Yes.
Let's demystify rope.
ROPE stands for rotary position embedding.
Okay.
To understand why it's necessary, we have to remember that transformers do not naturally read text left to right the way humans do.
They process it all at once.
They process all the words in a sequence simultaneously. Because of this, they need a mathematical mechanism to understand the order of the words.
Right.
They need to know that the dog bit the man has a fundamentally different meaning than the man bit the dog.
Even though the words are identical.
Exactly.
It needs a coordinate system for the sentence.
Precisely. ROPE provides that coordinate system, mapping the position of every token.
But what happens when the window gets huge?
When you expand a context window to something as massive as 128,000 tokens, the standard ROPE mapping starts to lose its resolution.
Like stretching an image.
Imagine drawing a highly detailed map on a small piece of paper and then stretching that paper out to the size of a billboard.
The lines get blurry.
Exactly. By increasing the base frequency dial to 500,000, they essentially gave the model a much higher resolution coordinate system.
So it doesn't lose its place.
It allows the model to maintain a precise, pinpoint understanding of where every single word is located within a massive document.
Ensuring it never loses track of its place, even in a whole book.
Right.
Okay, so we have established this massive, highly stable, dense brain.
Yep.
It has an optimized memory system and the ability to read whole books at once without getting lost.
That's the architecture.
But a brain is only as good as the information you feed it.
Always.
Let's transition to the data engine and the remarkable scaling laws they utilized.
The scale here is hard to fathom.
Because the sheer volume of data is almost impossible to conceptualize, they put this model on a 15.6 trillion token diet.
Trillion with a T.
That is almost 50 times more compute spent on pre-training than we saw in previous generation models.
The scale is staggering. But the raw number isn't the most important factor.
No.
The composition of those 15.6 trillion tokens is where the real engineering breakthrough lies.
Ah, okay.
If we connect this to the bigger picture of where AI is heading, you simply cannot just scrape the internet, dump the raw text into a server, and expect a frontier model to emerge.
It's garbage in, garbage out.
Precisely. The data mix they finalized was highly deliberate.
What was the breakdown?
Roughly 50% general knowledge.
Okay.
25% mathematical and reasoning tokens.
Yep.
17% code, and 8% multilingual text.
I want to pull on that thread because that breakdown is incredibly telling.
It is.
Almost half of the training data isn't conversational text or encyclopedia articles. It's code, math, and strict logic. Why feed a chatbot so much math?
Because it represents a strategic shift in how we cultivate intelligence in these systems.
How so?
The industry has realized a profound truth over the last year. Teaching a model the rigid, unambiguous, rule-based structures of computer code and mathematics actually improves its general reasoning capabilities across the board.
It's like teaching a kid to play chess so they become better at strategic planning in life.
That is exactly the dynamic.
That makes total sense.
If a model deeply understands the logical flow, the dependencies, and the strict syntax of a Python script,
right,
it somehow becomes better at constructing a cohesive, logical argument in a legal document or a philosophical essay.
It is utilizing logic and structure as a bridge to elevate general intelligence.
Exactly.
And obtaining that kind of pristine, structured data is a monumental task.
It's the hardest part of the job.
The curation process outlined in the technical details is fascinating. It's not just a basic web scraper mindlessly downloading pages.
Though they had to be surgical.
They built highly customized HTML extractors that optimize for removing internet boilerplate while keeping the actual valuable content.
Right.
But my favorite specific detail is that they deliberately engineered their extractors to keep the alt text from images on mathematics websites.
Which is brilliant.
Why? Because that is exactly where the latex formulas hide.
Yes.
It's such a brilliant surgical approach to extracting human knowledge.
It really highlights that at this frontier level, data engineering is arguably just as critical, if not more so, than the neural network architecture itself.
You have to scrub the noise out of the signal.
You do. They implemented 3 distinct, rigorous levels of deduplication to ensure the model wasn't just memorizing the same repeated internet garbage.
Break those down for us, because deduplication sounds simple until you apply it to 15 trillion tokens.
Right. First, they use URL-level deduplication.
Okay.
Keeping only the most recent version of a web page and discarding older, outdated snapshots. Second, they utilized document-level deduplication using a technique called global minhash.
What does that do?
It identifies and removes near duplicates. So articles that are slightly rewritten but contain the exact same information.
So it's not just checking for exact copies.
Right. And third, they went incredibly granular with aggressive line-level deduplication.
Line level.
Yes. They actually scoured the data set and removed specific lines of text that appeared more than 6 times within a given 30 million document bucket.
Wow. So that strips out the repetitive navigation menus.
The cookie warning banners.
The subscribe to my newsletter footers that would otherwise completely dilute the model's understanding of human language.
Exactly. It cleans the text up beautifully.
But they didn't stop at just removing duplicates, did they?
No. They also used sophisticated heuristic filtering. One of the primary tools they deployed was measuring the Kullback-Leibler divergence of token distributions.
Okay, let me pause you right there.
I know, it's a mouthful.
Because Kullback-Leibler divergence sounds like a warp drive component from a science fiction movie.
It does.
We need to translate that. What is it actually doing?
Let's frame it simply. Think of Kullback-Leibler divergence as a highly sensitive weirdness detector.
A weirdness detector, I like that.
We have a strong mathematical baseline of what the vocabulary and word frequency of a normal high-quality article looks like.
Okay.
If a scraped web page has a bizarre spike in random letters or a massive repetition of spam keywords, its mathematical shape looks fundamentally different from normal text.
Right.
KL divergence measures that exact difference in shape.
So it's looking at the geometry of the words.
Basically, it allows the automated systems to instantly identify and throw those bizarre, low-quality pages into the trash without a human ever needing to read them.
Oh, weirdness detector. I love that. And yet, even with the weirdness detector, they still needed more refinement.
They needed to judge the actual quality.
Right. They moved on to model-based quality filtering. And this is where it feels incredibly futuristic.
It's wild.
They literally used their earlier, slightly smaller models, like the previous 70 billion parameter versions, as judges.
Yep.
They had those models annotate vast swaths of data to train incredibly fast classifiers, specifically Distill-Roberta models, to score the educational quality of billions of web pages.
It's AI grading the homework.
It is literally artificial intelligence curating the curriculum for the next smarter generation of artificial intelligence.
This is a profound structural shift in the industry. We are fundamentally bottlenecked by human annotation at this scale.
Because there's just too much text.
You cannot hire enough human beings on Earth to read and grade 15 trillion tokens.
It's impossible.
Using predecessor models to bootstrap and refine the data quality for successor models is not just a neat trick. It is the only viable path forward for these massive training runs.
But this reliance on massive scale brings up a huge financial and logistical risk.
Massive risk.
If an organization is spending hundreds of millions of dollars on compute time, how do they know that a 405 billion parameter model is the right size before they train it?
They have to be certain.
You can't just throw darts at a board when the electricity bill is the GDP of a small island.
You absolutely cannot guess. And this brings us to one of the most critical engineering innovations in the entire project.
Which is?
Their advancement of scaling loss.
Okay, explain that.
Traditionally, Scaling laws, which are mathematical formulas that predict how a neural network will perform as you increase the compute, they only predicted a metric called next token prediction loss.
Basically, how good the model is at guessing the next word in a sequence.
Exactly. But knowing the loss doesn't actually tell you if the model will be any good at solving a complex calculus problem or writing a functional Python script.
Right. There's a massive disconnect between being good at autocomplete and passing the bar exam.
Precisely. So this team developed a highly sophisticated two-step scaling law methodology to bridge that gap.
How did they do it?
First, they established a strict mathematical correlation between compute optimal models and their negative log likelihood on specific downstream tasks.
Okay, let's simplify negative log likelihood for the listener.
Think of it as a measure of the model's surprise or uncertainty.
Okay.
A lower negative log likelihood means the model is highly confident and accurate in its understanding of a specific topic.
Got it.
So first they mapped that. Then the second step was correlating that likelihood with actual real-world benchmark accuracy.
Using what?
Using smaller, older models as a bridge to establish the pattern.
So they are building a predictive bridge.
Yes. By mapping these what we call isoflops curves that show performance for a given amount of compute, they could accurately predict the downstream benchmark accuracy on complex tasks.
Before they even started.
Before the massive 16,000 GPU cluster was ever turned on.
That's incredible.
They looked at the math and realized that the curve at the extreme high end of compute was flat enough that they could safely choose exactly 405 billion parameters.
And they knew it would work.
And know with high confidence exactly what real-world performance they would get for their investment.
That level of predictability is wild to me. It is like knowing exactly what a child's SAT score will be the day they are born based solely on the nutritional content of their diet.
It's exactly like that.
And speaking of the end of the training cycle, we have to talk about the secret sauce they applied right at the finish line.
Annealing.
Annealing. In the very last stage of pre-training, representing the final 40 million tokens out of the 15 trillion.
A tiny fraction.
Right. They dropped the learning rate down to 0.
Yeah.
And they fed the model an ultra high quality, benchmark-free mix of data. What does dropping the learning rate actually do?
Annealing is a fascinating and highly effective technique. In neural network training, the learning rate determines how drastically the model updates its internal weights when it encounters new information. By dropping the learning rate linearly to 0 over those final 40 million tokens, you are essentially telling the model, stop making large, sweeping changes to your fundamental understanding of the world.
Just tweak the edges.
Exactly. Just perform fine-grained, microscopic refinement based on this pristine data.
It's the final polish on the gemstone.
Beautiful way to put it.
But what I found highly revealing in the technical breakdowns is the differential impact this annealing process had. For the smaller models in the herd, like the 8 billion parameter version, annealing provided massive sudden gains.
Right.
Like a 24% improvement on the GSM-8K math benchmark just from this tiny final phase.
Huge jump.
But for the massive 405B model, the improvements from annealing were practically negligible. Why the difference?
It is a phenomenal insight into model capacity.
How so?
It suggests that at 405 billion parameters, the model has derived such incredibly strong intrinsic reasoning capabilities from the sheer scale of the massive pre-training that it doesn't need specific upsampled high-quality domains at the very end to figure out how to solve those problems.
I already know how.
The capacity of the brain is so large that the knowledge and the logical pathways are already fully internalized.
The smaller models needed the final hint.
The big model already understood the assignment perfectly.
That's fascinating. Let's pivot from the theoretical math to the physical grounding reality of this endeavor.
To hard work.
Yes. We keep throwing around the phrase 16,000 GPUs. Let's really paint a picture of this for you, the listener.
It's hard to grasp the scale.
We're talking about 16,000 highly advanced H100 GPUs.
Right.
Each one running at roughly 700 watts.
It's a power plant.
The power consumption, the heat generation, the intricate networking required just to keep them talking to each other.
It's essentially the infrastructure of a small city dedicated entirely to matrix multiplication.
Exactly.
The physical infrastructure required to pull this off without catastrophic failure is just as much of an engineering marvel as the neural network architecture itself.
So how do they connect them all?
To connect all these processors, they had to build a custom ROC network.
ROCE. What is that?
That stands for RDMA over Converged Ethernet, and they coupled it with NCCLX,
Which is?
a highly customized fork of an existing collective communication library.
Why do they need a custom network? Why not just plug them all into a massive switch?
Because when you are splitting a single mathematical model across thousands of distinct physical machines, the network latency becomes your single biggest bottleneck.
Network latency. So the time it takes for data to move.
The microscopic amount of time it takes for one GPU to transmit a calculation to another GPU.
Okay.
If the GPUs are waiting for data to arrive over the cable, they aren't doing math.
And if they aren't doing math?
That is wasted money.
Yeah.
This custom network and library were specifically designed to handle communication latencies on the order of tens of microseconds,
Microseconds.
ensuring the massive flow of data never stalls the training process.
And they absolutely had to split it because a 405 billion parameter model does not fit on one GPU.
It doesn't even fit on a single massive server node.
How do they actually slice this dense brain up so that 16,000 different chips can work on it simultaneously?
Right.
The documentation refers to it as 4D parallelism.
You have to intelligently shard the model across 4 distinct dimensions to make the math work physically. Let's break them down.
Please.
First is tensor parallelism. This is slicing the brain at the most fundamental level.
Okay.
It splits the individual matrix multiplications, the core math operations, inside a single layer across different devices.
So if there is a massive equation, GPU A does the left half and GPU B does the right half at the exact same time.
Correct. The second dimension is pipeline parallelism.
How does that work?
Here, you partition the model vertically by its layers. One group of GPUs handles layers 1 through 10.
Okay.
The next group handles layers 11 through 20, and so on.
I want to dig into pipeline parallelism because it introduces a massive headache, right?
It really does.
If GPU Group 2 is waiting for GPU Group 1 to finish layer 10, aren't they just sitting there doing nothing?
Yes. That idle time is known as a pipeline bubble.
A bubble.
It is the bane of distributed training. To minimize these bubbles, engineers have to mathematically calculate incredibly precise micro-batch sizes,
Micro batches.
constantly feeding small chunks of data through the layers like a highly synchronized factory assembly line, so no station is ever waiting for parts.
A microscopic assembly line running at the speed of light.
Exactly.
What's the third dimension?
Third is context parallelism. Remember we discussed the massive 128,000 token context window.
The whole book.
Right. That input sequence itself is too large to fit in the memory of a single device during processing.
So they slice the input too.
So they slice the actual sentence or document into chunks and process those pieces in parallel across different GPUs.
And finally, the fourth dimension.
Finally, data parallelism using FSDP or fully sharded data parallel.
What does that mean in practice?
This dimension involves having multiple copies of the model, or more accurately, sharding the optimizer states and gradients across the entire cluster.
Okay.
So that different groups of GPUs can process entirely different batches of the 15 trillion tokens simultaneously and then synchronize their learnings.
It is genuinely like having 16,000 highly trained chefs cooking a single, incredibly complex, multi-course meal.
That's a great analogy.
And they all have to pass ingredients to each other in microsecond intervals without ever bumping into each other or dropping a plate.
Exactly.
Which leads me to a reality check that absolutely blew my mind when I read it.
The failure rates.
During the 54-day continuous training run, there were constant interruptions.
Oh, yeah.
And a staggering 78% of those unexpected interruptions were purely hardware issues.
Yep.
GPU failures, massive memory errors, silent data corruption, networking blips.
The hardware was screaming.
But despite that daily chaos, they achieved over 90% effective training time. How is that even possible?
It is a testament to their obsessive fault tolerance engineering.
Because usually, if one node fails, everything fails, right?
In a synchronous distributed training run, if even one single GPU out of the 16,000 fails, the entire training job halts immediately.
So what did they do?
You have to write an automated system that detects the failure, isolates the bad node, reboots the affected systems, loads the last checkpoint from the storage fabric, and resumes the math. Automatically. Achieving 90% uptime when you have hardware literally burning out on a daily basis requires an incredibly robust checkpointing and recovery system.
How often are they saving?
They had to engineer a storage solution capable of saving the massive multi-terabyte model state in seconds.
In seconds?
Ensuring that writing the backup to disk didn't pause the GPUs for too long, thereby minimizing lost work.
So after 54 days of pushing silicon to its absolute physical melting point, they finally have the pre-trained model.
The base model, yes.
But as we know in this field, a raw pre-trained model is essentially just an autocomplete engine on steroids.
It's very smart, but very chaotic.
It might know everything on the internet, but it doesn't act like an assistant.
Yeah.
It doesn't know how to answer a question politely or format a response.
Right.
This brings us to post-training and alignment. And here, the team made a massive, highly debated design choice that we need to highlight.
Yes, they did.
They completely rejected RLHF.
This is an incredibly crucial point for the machine learning practitioners listening.
Explain why.
RLHF, which stands for Reinforcement Learning from Human Feedback, has been the undisputed gold standard for aligning models ever since the mainstream breakthrough of chat interfaces.
Right.
RLHF uses a secondary reward model to score the AI's outputs, and then it updates the main model's behavior using highly complex reinforcement learning algorithms.
Typically proximal policy optimization, or PPO.
Exactly.
If I can use an analogy here, because PPO is notoriously dense, I always picture RLHF like training a dog using a highly complex shifting point system.
Okay.
The dog has to figure out exactly how many abstract points a specific trick is worth, and the rules of the game keep changing slightly based on the reward model's mood.
Right.
It works eventually, but it's exhausting and prone to bizarre behavior loops.
That is a very apt analogy. RLHF is notoriously unstable. It is heavily sensitive to hyperparameters.
And it causes weird outputs sometimes.
It can lead to reward hacking, where the model figures out how to cheat the scoring system without actually giving a better answer.
Right.
And it is exceedingly difficult to scale reliably. Going back to their philosophy of managing complexity, the team decided to bypass it entirely.
So what did they use instead?
Instead, they relied on supervised fine-tuning, rejection sampling, and direct preference optimization, or DPO.
Walk us through DPO, because it seems so much simpler on the surface.
DPO removes the complex, unstable reward optimization loop entirely. Instead of generating abstract scores, you simply collect human annotations, where human looks at two responses and says, response A is better than response B.
Just a simple preference.
DPO takes that data and directly updates the mathematical weights of the model to increase the probability of generating response A and decrease the probability of response B.
It's much more direct.
It is a direct, stable mapping of human preference.
So, using the dog analogy, instead of a complex point system, DPO is just putting two options in front of the dog and explicitly saying, do this one, not that one.
Exactly. It scales beautifully.
And they combine this with rejection sampling.
Yes. They coupled this with a technique called rejection sampling that would have the model generate dozens of different responses to a single prompt.
Okay.
Use a reward model simply to pick the absolute best one out of the batch, and then use that pristine response as high-quality supervised fine-tuning data for the next round.
So it's generating its own perfect examples.
This combination achieved incredible alignment results without the massive headaches of reinforcement learning.
And they pushed specific high-value capabilities incredibly hard during this alignment phase. Let's look at their approach to code.
The code execution loop.
They didn't just have human programmers sit down and write Python to train it. They used an expert code model to generate millions of synthetic programming problems and solutions.
Right.
But they took it a critical step further, didn't they?
Yes. The innovation here is the execution feedback loop.
What does that mean?
They didn't just trust the generated code. They actually ran the synthetic code through static and dynamic analysis tools.
They actually ran it.
They compiled it, executed it, and checked if it actually solved the stated problem without throwing an error.
And if it worked.
If the code worked flawlessly, it was fed back into the training data. The model is literally testing its own homework.
That's amazing.
This grounds the synthetic data in absolute objective truth. A piece of code either runs or it doesn't. There is no ambiguity.
They applied a similar rigorous logic to math and reasoning capabilities.
They did.
The details show they used Monte Carlo tree search to generate valid step-by-step reasoning traces.
Yes.
Now, Monte Carlo tree search sounds like a strategy for beating a casino game. Break that down for us. What is the Monte and what is the tree?
The name does actually originate from the randomness of casino games.
Really?
Yeah. In this context, it is a method for exploring complex probabilities. Imagine a highly complex math proof.
Okay.
At any given step, there are multiple possible logical paths you could take. Some lead to the answer, some lead to dead ends.
Right.
This branching structure is the tree.
Okay, so how does the model navigate the tree?
The Monte Carlo aspect involves the model randomly exploring these different branches of logic to see where they lead.
Like testing out different moves in chess.
Exactly. But they didn't just let it wander aimlessly. They paired this search with stepwise reward models.
Stepwise meaning at every step.
So at every single line of a generated math proof, a secondary model acts as a harsh judge.
Evaluating what?
Evaluating, is this specific step mathematically and logically sound? If a branch introduces a logical fallacy, it is instantly severed and aggressively filtered out.
So it's pruning the bad ideas in real time.
Yes. The model only learns from the complete paths that successfully navigate the complex tree to arrive at the correct answer.
Which is brilliant.
The profound thing here is that they're not just teaching the model what the final answer is. They are explicitly teaching the model how to construct a flawless chain of thought.
And the capabilities don't stop at pure thought. There is tool use, which is the bridge that transforms this technology from a static chatbot into an active agent.
The agentic capabilities.
This model natively knows how to use a Python interpreter, how to query the Brave search engine, and how to interface with Wolfram Alpha.
All built in.
It's not just generating text, it's capable of writing a multi-step execution plan.
The implications for workflow automation are immense.
Right. It can literally output a plan saying, first, I am going to search the web for the latest economic data. Second, I will write and execute a Python script to parse the tables from that data.
And then?
Third, I will pass those parsed numbers to Wolfram Alpha to solve the complex differential equations.
It handles the whole pipeline.
It calls a tool, reads the output, realizes what it needs to do next, and calls another tool. All zero shot, without being explicitly prompted step by step.
But equally important to what the model can do is a concept they focused heavily on during this alignment phase.
Which is?
Factuality. Or, as they phrase it in the design philosophy, teaching the model knowing what it knows.
Knowing what it knows.
One of the biggest, most persistent criticisms of large language models is their tendency to hallucinate.
Oh, yeah.
To confidently invent plausible sounding information when they don't actually know the factual answer.
Confidently incorrect. We all know that guy at a dinner party who just makes up statistics to win an argument.
We do, and it is a major barrier to enterprise adoption. To combat this, the team deployed a technique called knowledge probing.
How does that work?
They would extract snippets of highly specific factual data from the pre-training corpus, generate obscure questions based on them, and ask the model to answer.
Okay.
Crucially, they simultaneously evaluated the model's internal mathematical confidence levels.
So they can see the model's inner doubt, even if it's trying to sound confident.
Exactly. If the model's internal probability of being correct was low, they explicitly trained it to output phrases like, I don't know, or I cannot answer that with certainty.
Wow. So they trained it to admit ignorance.
They are actively aligning the model to refuse to answer rather than guess. It is enforcing epistemic humility at the fundamental weight level of the network.
Enforcing epistemic humility. I absolutely love that phrasing. I need to install that update in a few people I interact with.
Don't we all?
But here is where the technical details get really interesting, moving beyond just text and logic.
The multimodal experiments.
Yes, the process of giving this model vision and speech. The big surprise to me is that they didn't build this as a native multimodal model from scratch.
Right.
The way some competitors have claimed to do, where images and text are mixed from day one. They used a compositional approach. Why build it in pieces?
The compositional approach is an incredibly elegant and pragmatic engineering solution.
Why not just train it all together?
Recreating an entire 405 billion parameter model from scratch on a mixed diet of images, audio, and text would be astronomically expensive.
Oh, because they're starting from zero.
And it carries the severe risk of degrading its hard-won text reasoning capabilities.
Right.
You don't want to break the math genius just to teach it how to look at a picture. So they froze the core 405B language model. The weights are locked in, they cannot change.
The brain is sealed in a jar.
Exactly. Then they trained completely separate, smaller neural networks to act as encoders for images and speech. And to connect them, they introduced adapters.
Adapters, meaning layers of cross-attention that basically act as translators between the visual or audio cortex and the main frozen language brain.
Yes. Let's look at vision and video.
Okay.
The imaged actor takes the raw pixels, processes them into visual token representations, and feeds those tokens directly into the language model's processing stream.
And what about video? That's way more data.
For video, they didn't just brutally feed it thousands of raw frames, which would overwhelm the memory. They trained a temporal aggregator on top of the image adapter.
A temporal aggregator. How does that handle the flow of time in a video?
It allows the model to process a 3-minute video highly efficiently by looking at just one frame every 3 seconds.
Just one frame every 3 seconds.
It aggregates that temporal information, compresses it, and passes it to the language brain.
So it gets the gist of the action.
Allowing the model to answer complex causal questions about the sequence of events in the video without drowning in redundant pixel data.
And the speech understanding and generation approach is even cooler, in my opinion.
It's very impressive.
Because it doesn't just listen to your voice, transcribe it to text like a traditional dictation software, and then read the text. It processes the raw audio natively.
This is a critical distinction for achieving low latency and capturing emotional nuance.
How does it work?
The speech adapter feeds the acoustic token representations directly into the language model.
Okay.
This means the model doesn't just understand the spoken words. It understands the tone, the size, the pauses, the sarcastic inflections.
Because it's hearing the audio, not reading the transcript.
Exactly. And for the output generation, they completely bypass the language model's text generation mechanism.
Wait, it doesn't write out a sentence to speak?
No. They pipe the internal model embeddings, the raw mathematical representation of the abstract thought it wants to convey, directly into a streaming prosody text-to-speech engine.
Meaning the voice output has real-time emotional inflection and pacing.
Right.
If the model is mathematically generating a somber or sad story, the embeddings inherently parry that semantic weight.
And the text-to-speech engine outputs a somber voice instantly.
Without waiting for the whole sentence to be written out as text first, that is sci-fi level seamlessness.
It fundamentally changes the user experience. You are no longer interacting with a text processor. You are conversing with an entity that processes and outputs emotion natively.
That is wild.
But of course, all these fascinating architectural choices and capabilities mean nothing if the model doesn't perform in the real world.
Right. Let's look at the benchmarks and the reality of deploying this beast.
It's time to look at the scoreboard.
On the standard, rigorous academic benchmarks, this 405B dense model either matches or outright beats the leading proprietary models across the board.
It's highly competitive.
We're talking MMLU for massive multitask general knowledge, Human Evil for complex coding, GSM 8K for grade school and advanced math. It is dominating the charts.
It proves the thesis we started with. Open weights can absolutely achieve frontier-level intelligence.
But let's be real for a second. Can anyone listening to this actually run it?
We have to provide the critical, honest assessment here.
Please do.
While the zero-shot and few-shot benchmark numbers are undeniably incredible, the physical compute required for a practitioner to actually run inference on a 405 billion parameter dense model is staggering.
How bad is it?
At standard BF16 precision, this model simply does not fit on a single standard server equipped with 8 H100 GPUs.
Doesn't even fit.
You need multiple massive nodes communicating constantly via high-speed networking just to generate a single word.
That physical reality prices out 99% of independent developers and smaller enterprises.
Which brings us to their highly technical solution for the rest of us, FP8 quantization.
Okay, FP8 quantization.
By reducing the precision of the numbers in the neural network from 16-bit to 8-bit, they essentially shrink the memory footprint of the model by half.
Let me ask the obvious question, though. You are basically taking the highly precise decimal points in the math and rounding them down so the file size is smaller. Doesn't that lobotomize the model and make it stupider?
It absolutely can degrade the model's intelligence if done carelessly.
So how did they avoid that?
That is why their quantization approach was highly surgical. They did not compress the entire brain.
What did they compress?
They only applied FP8 quantization to the feed-forward networks inside of layers, which are essentially the raw knowledge storage areas, and account for about 50% of the total inference compute.
Okay.
Crucially, they left the self-attention layers, the parts of the brain that connect complex ideas together, and the very first and last layers of the model completely unquantized at full high-definition 16-bit precision.
So they compress the encyclopedia, but keep the reasoning engine fully intact.
Exactly. And they went further. They implemented dynamic scaling factors.
What are those?
When a model processes highly unpredictable tokens like specific dates, rare words, or complex math symbols, the internal activation numbers can spike wildly.
Okay.
If you're operating at 8-bit precision, those spikes can cause mathematical underflows where the number just drops to 0 and corrupts the thought process.
Oh, that's bad.
The dynamic scaling adjusts the precision bounds in real time to prevent those errors.
That's incredibly clever.
This surgical approach allows the model to fit on fewer nodes, making it dramatically more accessible to practitioners while almost perfectly preserving its benchmark-topping reasoning capabilities.
And as with any model this unprecedentedly powerful, safety is a massive part of the conversation and the documentation.
Absolutely.
The release details extensive, rigorous evaluations around cybersecurity risks and chemical, biological, radiological, nuclear, and explosives, or CBRNE risks.
We want to report these findings impartially, exactly as the extensive safety testing presents them.
Right.
The authors conducted months of red teaming with external domain experts to determine if giving the public access to this model would increase the likelihood of a bad actor being able to create chemical or biological weapons.
And what were the results?
The empirical results of the study show that the model does not provide a statistically significant uplift in risk compared to what a bad actor could already find using a basic web search.
So it's not giving them new ideas.
The factual information is already out there on the internet.
Yeah.
The model does not magically create new, unknown weaponization protocols.
They also evaluated the cybersecurity threat landscape, testing if the model could act as an autonomous hacking agent.
Yeah.
The results showed it was quite adept at network reconnaissance, mapping out systems, but it consistently failed to successfully execute complex exploits autonomously.
That's reassuring.
However, the teams did acknowledge some clear, persistent limitations. The model is still vulnerable to text-based prompt injections.
Complying with explicitly malicious prompts around 21% of the time in their stress tests.
Right. So to mitigate this at the deployment level, they released Llama 3 alongside the main model.
Which is crucial.
This is an 8 billion parameter model specifically fine-tuned to act as a system-level filter, actively categorizing and blocking unsafe inputs and outputs before the end user ever sees them.
It is a pragmatic acknowledgement that the core foundational model cannot be made perfectly, inherently safe without lobotomizing its reasoning capabilities.
You can't make the brain perfectly safe without making it dumb.
Exactly. Therefore, robust system-level safeguards like input-output filtering are absolutely essential for anyone looking to deploy this technology in a public-facing production environment.
So bringing this all together, what does this massive technical achievement mean for you, the listener? Let's bring this down to practical, everyday implications.
It means a lot.
If you are an enterprise or a researcher, you now have open, unrestricted access to top-tier reasoning.
You can download the actual weights.
You can fine-tune it locally on your own proprietary, highly sensitive data, and you fully control your data privacy without ever sending a single packet of information to a corporate API.
That's the biggest shift.
Furthermore, because of the relentless way they trained this entire herd of models, the smaller 8B and 70B parameter versions punch way above their weight class.
They really do.
They were effectively overtrained on the 405B's meticulously curated, high-quality data engine.
Which means what?
This means you can run incredibly smart, highly capable models right on edge devices like laptops or local servers. The barrier to entry for utilizing frontier intelligence just went to essentially zero.
The democratization of this level of compute and the widespread availability of this algorithmic refinement will absolutely act as a catalyst.
Accelerating research and development across every vertical, from biotech drug discovery to quantitative finance to automated software engineering.
Exactly.
Which is the perfect transition into our final segment, Novel Notions.
I love this part.
Just a quick reminder for our listeners, this segment is for entertainment purposes only. We take the concrete technical mechanisms we just spent the last hour discussing and pitch outlandish but logically consistent future scenarios inspired by the trajectory of the technology.
Let's hear it.
I will kick us off. I do one. I call it the infinite sensory web.
Okay, let's explore it.
We discussed how the paper proved that the compositional adapter approach works flawlessly.
Right.
They bolted highly effective vision and speech modules onto a frozen 405B core brain without needing to retrain the massive core.
Using those adapters.
Because the weights are open and available to anyone, the global open source community is going to take this adapter mechanism and run absolutely wild with it.
I can see that.
Within 18 months, we aren't just going to see basic image and audio adapters. We are going to see thousands of bespoke, highly specialized sensory adapters.
The technical foundation entirely supports this prediction.
It does, right?
By freezing the massive language model and only training the thin cross-attention layers on text-to-sensor data pairs, the compute requirement is tiny compared to pre-training.
Right.
A small university lab could do it.
Right.
You just need a data set of the raw sensory input accurately mapped to a text description.
Exactly. So let your imagination run. Imagine a genomic adapter. You feed raw, unsequenced DNA data directly into the cross-attention layers.
And the model understands it natively.
The 405B model natively understands the genome, predicting protein folding or genetic disease markers without translating it to ACGT text strings first.
That would be revolutionary.
Or imagine a seismograph adapter natively reading tectonic vibrations to predict earthquakes.
Wow.
But the most immediate, highly probable scenario, a medical imaging adapter. Hospitals will train an adapter on millions of historical MRIs.
Right.
The model will see the raw voxel data of an MRI natively, spotting microtumors that human radiologists miss.
And combining that visual intuition with its 405B parameter medical textbook knowledge.
Exactly.
It completely reframes the utility of the technology. It turns the large language model from a sophisticated text processor into a universal multimodal pattern recognition engine capable of digesting the physical world.
It's going to happen.
That is a highly plausible and incredibly exciting technological trajectory. I have a second scenario to pitch to you.
Let's hear it.
Let's call it compute optimal abandonment in the century model.
Okay, I'm highly intrigued. Where are we going with this?
In the technical details, the engineers note a fascinating anomaly. They explicitly state that they trained the 8 billion parameter model far past the point of being considered compute optimal.
Right.
According to established scaling laws, they should have stopped training it much earlier as the returns diminish.
But they kept going.
But they stubbornly kept feeding it trillions of tokens of data just to make it ridiculously, disproportionately smart for its small physical size.
Why do that?
This highlights a deliberate trade-off. You spend massively more money on upfront training compute, but you get a small model that is incredibly cheap and fast to run during inference forever.
Right. You are aggressively front-loading the energy costs.
Precisely. My thesis is this. What if the industry completely abandons the race to scale up parameter counts?
Stop building bigger models.
What if this 405B model is effectively the physical cap of what is practical, and instead of building a 10 trillion parameter model, we scale training time infinitely? Imagine a global consortium builds a relatively tiny, hyper-efficient 1 billion parameter architecture. But instead of training it for 54 days on 15 trillion tokens, they trained it for 5 years straight on 100 trillion tokens, running it repeatedly through billions of simulated Monte Carlo reasoning trees.
A century model. The energy cost to train it for 5 years would be astronomical, bordering on a national infrastructure project.
The cost would be historic, yes. But once the training is done, the inference cost is practically zero.
Because it's so small.
You would possess a model that runs entirely locally on a standard smartwatch, requires almost zero battery power, but possesses the dense, flawlessly refined reasoning capabilities of a PhD.
That is insane.
If this scenario plays out, it entirely upends the current hardware market. The financial value shifts completely away from building massive cloud-based inference farms, because everyone is running genius-level models locally on their phones, and shifts entirely towards single, monolithic, multi-year training runs.
The business model of chip manufacturers would have to pivot from selling millions of chips for daily inference to leasing out massive, centralized clusters for decade-long training jobs.
Exactly.
That is a wild paradigm-shifting thought. A pocket-sized supercomputer, completely decentralized from the cloud. The open-source community could literally launch a Kickstarter to crowdfund the electricity for a 5-year training run.
It is an extreme extrapolation of the current trend, but mathematically, the compute optimal abandonment principle they demonstrated with the 8B model proves that this dynamic is theoretically possible.
I absolutely love it. Well, that officially wraps up our deep dive into this monumental landscape-shifting release. Thank you so much for joining us on this incredibly technical journey.
Thanks for having me.
Before we go, I want to leave you with one final provocative thought to ponder over your coffee. We spent time discussing how they explicitly train this model to know what it knows, to measure its own internal uncertainty and proudly output "I don't know" instead of hallucinating.
Right.
If a machine of this scale can be explicitly trained to express doubt, to pause and structurally acknowledge the limits of its own knowledge, are we finally moving past the era of confident AI hallucinations? And perhaps more importantly, as we begin to interact with these highly capable entities on a daily basis, will their automated epistemic humility eventually rub off on us? Something for you to ponder.
A fantastic question to end on. Goodbye, everyone, and remember to keep questioning your assumptions, whether they come from a human expert or a 405 billion parameter model.